I remembered. Okay, I think we are ready to get started. We have a full, that did it. We have quite a full time. We want to pack your brains with everything, everything we possibly can. So welcome again to age depth modeling of sedimentary deposits, GSA short course number 503. We have a really great session today, next Wednesday, and the following Wednesday for you. I wanted to mention also that this short course is sponsored by Earth Rates, and Lisa Park-Bausch will say something about that, and also by GSA Limnogeology Division. So if you have any questions, please put them in the chat, or you can raise your hand, or you can break in. Martin doesn't mind being interrupted. So just gonna go through, oops. So I did hit record. We will be recording this and post this and give you access as soon as possible. We also wanted to make sure to highlight GSA Rise. This is for respectful and inclusive scientific events. We also have Jennifer Nocerino from GSA listening currently. And if you have any concerns, Elizabeth Davis is on the call. She is our student representative, student volunteer for GSA, and you can message her if you have any concerns about something that's being said or any behavior. So we want to make sure that people show respect, keeping questions concise and on topic, being considerate, listening with an open mind, avoiding saying or doing anything that is likely to be construed as harassment or bullying. Sorry, my window just moved. Being inclusive, welcoming a diversity of individuals and their identities, valuing differing perspectives, and avoiding exclusionary comments and behaviors based on any identity-based factors. You can report concerns to this email address, or as I said, you can message Elizabeth Davis in the chat here, and I believe she put something in the chat to say that. And I also will put the link to the complete GSA Events Code of Conduct into the chat once I stop talking. Quick introductions of your hosts. Martin, would you like to introduce yourself? Martin is our star and the presenter here.
Hello, everybody. I'm Martin. I work in Belfast, Queen's University Belfast. I'm from Holland originally, so I have a bit of a funny accent because it's also mixed with Northern Irish now. My background is in biology, but I work with archaeologists, geographers, statisticians, and I've always liked uncertainties in paleoecology, and that's how I got to age depth modeling, which we'll be talking about in the coming weeks.
Thank you. Lisa Park-Bausch.
Hi, everyone. Sorry, I'm Lisa Park-Bausch. I am a professor at the University of Connecticut. I am currently the lead PI on the Earth Rates RCN, which is about to sunset. I'm hoping that you know of it and maybe have even been supported by it for workshops and short courses like this one. I'm also the past chair of Limnogeology Division, and we were the ones that kind of thought of this idea to convene this workshop and put together the team that you see here. So I just want to thank my colleagues, both in Earth Rates and in Limnogeology Division. And I'm glad everybody's here.
Thanks, Lisa, and thanks, Martin. I'm Amy Mirbo. I'm also a past chair of Limnogeology Division. And was at the University of Minnesota at LACCOR in the Continental Scientific Drilling Coordination Office, now the CSD facility, for about 1,000 years, and left 2 years ago to be an independent consultant doing grant coaching, evaluation, broader impacts, diversity and equity consultation, and things like that. I've been working with Bacon since 2010, and on and off working with Martin and helping to teach people. So I am really looking forward to this, and I'm really excited to see such a big group of everyone here. I will also be kind of in the chat. I will probably be, making comments in the chat. It's nothing that anybody needs to stop and take a look at, but if there are things that I think will be helpful for people to know, little explanations, side explanations, or comments, I might be doing that. And I'll be, Lisa and I will also be watching the chat and collecting up questions for Martin. But you can also, raise your hand. We'll try to be looking for that, but it's hard to see everybody in the entire, since we've got probably 50, we had 52 registrants, we've probably got about that many people on the call right now. So I'm going to turn it over to Martin. While we're doing that, any questions right now?
Perhaps I could just add, we will try to have a short break of around 5 minutes or so, about halfway, just to catch our breaths. Yeah. Shall I start sharing my screen? Can you all see that? Yeah. Okay. So I will be showing my screen, and to your sides, you will probably see something peeking out, and that's my R session, which we will hopefully sometimes be using. So for some of the slides, there will be code in blue, which it would be good if you were able to and follow the presentation on Zoom, and then also have R open to just go along and put in some of the code that will appear on your screen. So then we can have a bit of, even though we're all far away from each other, a bit of an interactive session. And if that doesn't work, please let us know, okay? Right, so the schedule is that today we'll be mostly focusing on radiocarbon dating. That's radiocarbon dating and calibration. And then towards the end, we have a very few slides just to get our heads into age modeling, or actually age depth modeling. So what do we do once we have a few ages of a deposit? What should we be thinking of incorporating, how to get a model? And then next week, we'll be looking at these age depth models, mostly Bayesian ones. We'll start off with a few classical ones, but then move on to Bayesian ones. And then after that, in the final session, we'll be looking at lead-to-10 dating using Plum, which is a Bayesian lead-to-10 dating age model, and also running your own course. So that will be quite interactive, and we'll see where it goes. Yeah. So the first two sessions, they are the presentation slides are available on the website that Amy has sent around. What's in there is the presentation as PowerPoint and also as ODP, and there's also the code, the R code that you could run. But we'll also look at that very same R code in this presentation, if it makes sense. Right? Okay, so today we'll be talking mostly about radiocarbon dating. If your method of dating is not radiocarbon, then this might be a little bit less relevant, but we'll still be talking about uncertainties, and that will still hopefully be relevant even if you're not using radiocarbon dating. We'll be touching a little bit on upon the history of radiocarbon dating, because I love to geek out about that. I'll try to keep that to just a few slides, and also really about assumptions, because there's so many assumptions for radiocarbon dating, and there's so many ways in which it can go wrong. and we have to be all aware of where things, how they can go wrong. Then there's this other thing in that radiocarbon dates on their own don't really work. They need to be calibrated, and we'll be looking at that as well. Why we do it, why we need to do it, and how we do the calibration. And then again, at the end, a few slides just to get our heads into age depth modeling. Yeah. So again, we're mixing the PowerPoint slides here with R code. So if it's possible on your laptop or your computer to have both the Zoom session open and an R session, then once blue R code appears on your computer, then we can, when it appears in the Zoom session, we can try to run that code and see what happens. Yeah. I myself, I'm not using RStudio. I'm using just a terminal here. And that's the same terminal you would have in the lower left bottom of your RStudio window. It's just, I just like to work this way. Also, it takes up less space on my screen than a whole RStudio window. And then what comes out happens over here. I hope you can all see that, and I can make it bigger if it's all too small. Okay, so if things go wrong, if things don't work, or if I go too slowly, well, that won't happen, or too fast, just let us know. And yeah, there will be, Amy and Lisa will be looking after the chat. So again, if something is unclear, let us know. We'll also ask you, I think during the break or at the end, yeah, bits that are clear and bits that that could require more explanation. Yep. Right. So to get started with radiocarbon dating or with any radiometric dating, we have to look a little bit at the periodic table of elements, which we're all, I hope, familiar with. And most of these elements actually have at least one stable form of isotope. Yeah, for example, you have hydrogen, which has just one proton, and that's for example this one. But some different isotopes of the same element have different weights, because, for example, for hydrogen, if you add a neutron, you get deuterium, and if you add 2 neutrons, you get cesium. And these different amount of protons to neutrons, some of those nuclei are very stable, perfectly fine, but some combinations are not very stable, and those atoms of those isotopes will tend to fall apart after some time. That can be seconds or minutes or years or many, many years. Yeah. Now, if you plot the amount of protons here and the amount of neutrons here, and then plot all the elements, and color code how stable they are. So the stablest elements are, say, here in the middle, or the most stable isotopes. But towards the edges, there will be the configurations, the combinations of protons and neutrons in the nuclei in the isotopes are in many cases very unstable, and over time they will simply decay. Yeah, and one of those atoms, one of those isotopes is radiocarbon. So radiocarbon is produced high up in the atmosphere when there are cosmic rays that arrive on Earth into the atmosphere. They collide with particles, and thereby they produce neutrons, which sometimes crash into nitrogen atoms. Of course, 80% or so of the atmosphere is nitrogen. And when a neutron collides with nitrogen 14, then it suddenly changes into C14, so a different element, and it expels a proton. This C14 doesn't survive for long. It quickly oxidizes into CO2 and becomes part of the carbon cycle. This C14 is an unstable atom. Over time it will be a point where it will decay back into nitrogen again. and that happens at a constant rate. Yeah. So as far as we can measure, and as far as we know, these decay rates of the different isotopes are constant. They're not influenced by the environment. For example, for radiocarbon dating, for the radiocarbon atom, we know that on average, the average lifespan of a radiocarbon atom is around 8,600 years. But we more commonly express that as a half-life, and currently it's known to be around 5,730 years, plus or minus something. The actual half-life itself doesn't really matter too much because, we use the calibration curve to take into account the half-life. And what the idea is that you start off with material which has, at T0, it has 100% of radiocarbon, and over time it will be less and less because of the decay. Okay? Good. So let's play a little bit in R now, and we're going to write some commands. For those who haven't written any functions or haven't written like these things in R, you might be perhaps a little bit intimidated by it, but later on, we will not actually be using this type of commands, but it's just to get our heads into how to work with R and just to see how half-lives work. Yeah. So if you have your R screen or your R Studio screen somewhere, and what we're going to do is we're looking at the first line here, the first blue line, which is a variable called year, YR. It's just something that I name. You can name it anything, but I decided to call it that. So we're going to create within R a variable. Yeah, and this variable, what it will be, I write a little arrow, so the little larger than sign and minus sign. That's little arrow which says what this variable will become. And what it will make it will make a sequence and then open brackets. And R works a lot with brackets because the sequence, sec, is one of the many functions within R which are very useful. And this one is to make a sequence of values. And I start a sequence with 0, and then have a comma. And then the next option is that I tell it that this sequence, which starts with 0, it will increase in steps. And the size of the steps by, in this case, is 5,730, which is the half-life of radiocarbon. And I then also tell R that I want this sequence to be of a length 10. I want to have 10 values. Length equals 10. Yeah, so I now have all the information, and I close the bracket. I close the sec function, and I press enter. Wow, nothing happened. That's because there was no error. R did what it was told to do. It made a function YR, year, which contains 10 values, but it doesn't really spit them out. It just says, okay, that's what I did. Now, did you all manage to get that in your session? Any problems? No? Good. Okay, so what we can now do is to type YR to ask R to show us what is in the variable. Yeah. So we just type the name of variable and press enter. And now we see there's a list of 10 values starting with 0, then 5,730, 11,460, and so on until we reach around 50,000. Yeah. So these are the 10 periods in time, the 10 half-lives of radiocarbon in this case. Yeah. Now, we already said that at T0, 100% is available. Yeah, but the half-life is So if you have a population of carbon C14 atoms, and if its half-life is 5,730 years, if you start off with 1,000 atoms of C14, after one half-life, half will be left. Yeah? And if you add another half-life, half of that will be left, etc. So that's what we're trying to do now. So we have this half-life, 0.5. And if we just put 0.5 and ask what it is, it's 0.5, 50%. Yeah. So 0.5, if we just use that 0 times, so if we do to the power of 0, 0.5 little thingy, I don't know what I call them in English. We call them roof in Dutch. 0.5 to the power of 0, and then press enter, becomes 1. So at T0 with a half-life, at 0 half-lives, you have 100% left. Yeah. Now, so one thing with your command window, if you use your up arrow on your keyboard, you can retrieve previously typed commands. And that's very useful because if you're like me, you're lazy with typing. And if you can avoid typing, that's very useful. So we're getting back the previous command, 0.5 to the power of 0. And we just delete the 0 and replace it with a 1. Yeah, 0.5 to the power of 1. And that's 0.5. So after one half-life, half is left. Then we go back again and replace the 1 by a 2. So then after 2 half-lives, half of half is left. And after 3, so 12.5% is left, etc. So we can make that a bit faster by just typing, just giving another name to some variable, the little arrow, and then say 0.5 to the power of 0, 1, 2, 3, 4, etc. We just simply open a bracket and then give all the numbers that we're interested in the numbers 0 to 9. And in our speak, that is 0, ... or what you call them, the column to 9. And then close the bracket. Yeah? And then press enter. And again, we don't see anything, but if we then ask R to show what half-lives is, then we see it starts off at 1, then becomes a half, and then a half of a half, half of a half of a half, etc., all the way to reaching very low numbers. Okay. Now, in order to see them together and the year and the half-lives, we can combine them together. So C bind, which is bind columns, bind variables together as columns. So we can have first year, and then the next value I want to combine as a column is half-lives. One other thing, if you want to avoid typing too much, is you can type a few initial letters of your variable and then use tab to fill in the rest. That's a very handy trick in R. So we have C bind, year, and half-lives. We close the bracket. And then we end up with a list with 2 columns. And we have, say, at year 0, we have a half-life of 1. At 5,730, we have a half-life of 0.5, etc., etc., etc. Yeah. Now I'm just going to go back to that command again, because I want to present the half-lives not as between 1 and 0, but as percent. So I just multiply half-lives by 100. So 100 times half-lives. And now we end up with these columns. Yeah, at year 0, we have 100%, 5,730, we have 50%, etc., etc. So after around 10 half-lives, when we're at 51,570, then we only have, say, 0.2% of radiocarbon left. And that's really more or less the limit of what we can date. Okay? I hope that went fine. Right. So if we use this type of equation, we can then see how over time, as time passes, there will be less and less radiocarbon left. Yeah. In this animation here, black is carbon, and most of carbon, so carbon has 3 natural isotopes, C12, which most of carbon is C12, 99%. C13 is only 1%, and C14 is a million of a millionth of each particle. Yeah, so very, very tiny trace amounts. But these amounts can still be measured, which we'll come back to later. And over time, there will be less and less radiocarbon left, but we can still measure it. But if you have a problem, for example, with a little bit of contamination with modern carbon, especially for old dates, then that can be very problematic, because if you add 10 particles to this final bit, then you'll get a totally wrong answer. Let's just do that one again. So for material back to the Holocene, so over the Holocene or back to 20, 30,000 years ago, it's a really, really good technique. And with care, it can also be used further back. But we always have to be mindful of contamination problems. These animations, they can also be downloaded from my website, and I've also added some URLs. You can also download them from Vimeo or YouTube if you want to. You're free to use them for any teaching or anything. Yeah. Right. So what happens in the carbon cycle? We've got these cosmic rays that collide high up in the atmosphere with nitrogen, and then produce C14. And that C14 then oxidizes to CO2. And it becomes part of the carbon cycle. Yeah, so CO2 goes along with all the other CO2, most of which is C12 CO2, a little bit of C13 CO2. And that CO2 is then part of the carbon cycle. It gets into the ocean, and through photosynthesis is taken up by plants. And most of the CO2 that's taken up by plants will be C12 CO2, a little bit will be C13 CO2, and a tiny bit will be C14 CO2. And then animals will graze the plants and will also more or less get that same amount, the same ratio of C14 to 12, to C12. When they're alive, plants and animals, C14 will decay, but animals are constantly topping up their C14 because they're still eating the plants, and plants also constantly top up their C14 through photosynthesis. But the moment that metabolism stops, when animals die, then this clock starts ticking. Yeah, then the C14 is any decay in C14 is not replenished anymore, and we've got then this decaying concentration of radiocarbon over time. And that's what we measure in order to estimate the radiocarbon age. Okay? Right. So this has been done since the late 1940s. There were lots of people working on nuclear physics, including Willard Libby, who in the late 1940s predicted that there should be radiocarbon produced high up in the atmosphere. They simply had no way of actually measuring it yet. And they predicted that there should be C14. And if there was C14, it could then possibly also be useful for radiocarbon dating. So he published papers in 1949 saying that, okay, there is this thing called C14. And then in 1951, I think, he published the first paper with a list of radiocarbon dates. It was a paper in Science, and where we'll come to that later. Where material of known calendar age, the radiocarbon concentration in that material was measured, and that way to check if that radiocarbon dating actually worked. So the original radiocarbon way to measure radiocarbon was to put it into a flask as a gas and then wait for days, weeks. And the few radiocarbon particles in the flask, in the CO2, would over time decay. And whenever it decayed, there would be, that event would then be measured. Yeah? So you needed to have your sample, you had to have large samples and long counting times. Now that's, most of the labs now don't do that approach anymore, but instead we measure the particles themselves, not the decay events, but the particles themselves. And that is done in an AMS. Here's our previous AMS, which was dismantled in December last year. And now we have a new shiny Ion Plus Mikadas, which is a, well, 2.5 times 3.5 meters sized machine. And it's very small and yeah, very easy to maintain, we hope. I won't get into much detail there now. What this machine does is samples are put in here, and then the carbon particles are accelerated. They're put into a beam, and they're through electrical currents. They're charged and going to very high speeds. And then at several points there are magnets, very strong magnets, and that deflects the particles. Yeah, you can see that here. So particles could come in as a beam with a mix of C12, C13, and C14, but the magnet bends them. Yeah, and when they're bent, heavier particles like C14 will take a different route than lighter particles like C13 and C12. So we separate the beams of C12, C13, and C14, and then measure at the end of each beam, of each sub-beam, we measure how many particles arrive. And that way we can calculate how many radiocarbon atoms are still left in a sample, or more the ratio. All right. But say, originally this was done through decay counting. And so in 1951, Arnold and Libby published this first list of dates in Science. I think it's a really fascinating paper to read if you can find it. It's online, available online in Science. And those guys, they went to, they contacted people in different musea and asked for material of known historical age. For example, here in light blue, there are several Egyptian coffins and other pieces of wood from coffins, from boats, that were otherwise dated through historical information. So they were precisely dated, sometimes to the very year. They could say what the calendar age of that material should be. They also used dendrodated trees supplied by Douglas, I think. And those were dendrodated, so trees deposit yearly rings, and those yearly rings were counted back, and that way calendar ages could be obtained. Also, they asked from researchers over here in Europe if they could supply some organic material from known archaeological sites. For example, hazelnuts from a site that was otherwise known to be of a certain time span, like early Holocene. There, the uncertainties are quite large of the timing, but they could get some estimate. Now, if you then measure the radiocarbon age in each of those samples, you can see there's quite a good correlation between the known calendar age and the radiocarbon age that I measured in 1951. The dashed line here is the 1-to-1 line. So if radiocarbon age were exactly the same as calendar age, then they should be on that line. they're not exactly on it. So there's some dates that are way too young, others are too old. But generally, there is quite a good relationship between the two. I've put into this graph as well the current most recent calibration curve, which gives for each calendar year the corresponding radiocarbon year for the Northern Hemisphere atmosphere. And you see it's quite a good relationship between those original very first dates and our current knowledge of how radiocarbon age and calendar age coexist. Okay, right. So now let's go to the assumptions. Let me just check here. Yeah, I feel right on time. So let's talk about assumptions involved in radiocarbon dating. The first one is about that what we're assuming is that the atmospheric radiocarbon levels over time have remained constant. Yeah, so we can simply use at T0 as or the concentrations at T0 have been constant. They're not changing over time. As we'll see, this assumption does not hold at all. So we need to correct for this temporal changes in atmospheric radiocarbon levels. The second assumption is about well-mixed carbon reservoirs, and in some cases that is also not, this assumption is also not met, and also that the target event is dated, which is sometimes the case, but also not always the case. We'll look at each of them. Okay, right. So Libby already showed that that radiocarbon ages agree more or less with calendar ages, but we needed more information. Yeah, so since the 1950s, many people, many labs have been continuously trying to produce more values to put in that graph that relates calendar age to radiocarbon age. And most useful have been trees, so dendrodated wood, say blocks of 10 to 20 years, which were then of exactly known calendar age. And then those blocks were then radiocarbon dated to see how radiocarbon age and calendar age compare. Yeah. And what we found is that there's not a clear 100% one-to-one relation, but there's actually several wiggles in this curve that relates calendar year to radiocarbon year. And these wiggles, they can be seen here. If we just look at the Incal 20, so the latest Northern Hemisphere calibration curve over the past 1,000 years. So working here in cal years BP, which is calendar years before the present, and the present here is 1950, which is a bit confusing. 1950 seems like a strange year to call the present. But actually, we just saw that the very first radiocarbon dates that were measured in 1950. So that 1950 is actually a nice period to keep as an anchor. The radiocarbon community decided to stick with that date, AD 1950, as the T0. Other communities have decided differently. For example, ice cores are often measured as years before the year 2000, AD 2000. And say lead-210 dating expresses everything against the year in which it was measured, in which the lead-210 was measured. So it's quite important to be aware of that, those distinctions of what the different timescales are. Anyway, we see here many different data sets of trees that were measured. So trees from all over the world, mostly the Northern Hemisphere, but yeah, also New Zealand. So trees were taken from different places and were dendrodated and then also radiocarbon dated in a number of different labs. So the black ones here is trees from Seattle, measured in Seattle. Then in red, we've got, they're hard to see, but those were oaks, Irish oaks measured in Belfast. Then we've got in green some trees from Waikato in New Zealand and some other trees, yeah? Including some new ones in Tokyo. And, oh no, my cat wants food. I hope, okay, never mind. So in Japan, there's sometimes a little bit of an offset with what we see happening in Europe. And that's something that we're actively looking at. So, although originally the trees were measured, say, in blocks of 10 to 20 years, because we needed that amount of wood in order to get sufficient amount to radiocarbon date with decay counting. Now with the recent AMS, we can actually get tiny slivers of wood, just 1 year of wood. So recently, many labs have been working on getting yearly dates. Hi, Amora. Hi, that's my cat. I'm not picking her up because she will get angry. Yes, go get food. All right, so you see there's the data sets, they more or less agree. There's a bit of scatter around the mean curve. And it's this curve, the intercal 20 curve, which is an approach to get all those data sets together and try to get an average, an estimate of what the radiocarbon age has been over time. Okay? Right. So this is just the most recent 1,000 years, but you can go back further in time. So with tree rings, we can get reasonably accurate and reliable data sets all the way back to 14,000 cal-BP. Beyond that, in the Ice Age, there's simply not enough trees left to reliably do dendrodating. And the trees are probably very stressed, and so the rings are not very easily replicated. But say for 14,000 cal-BP up to 0 cal-BP, we've got a very well replicated record for the calibration curve. And yeah, it's many of those results are very well replicated. There's some issues in that some years have seen events of enormous peaks in radiocarbon. And with the intercal 20 curve, we tried to have this curve so like stable enough, but also sensitive enough to be able to pick up those peaks as well. Okay. So there's also another curve for the Southern Hemisphere, which is partly based on data for the Southern Hemisphere, and then also based on data for the Northern Hemisphere with an offset applied to it. And then we also have the marine curve, which does the same, where this data has then gone through a marine model, which tries to express what happens in the marine environment with radiocarbon ages. Okay, so that goes back to 14,000 years. But we want to go further back, yeah, because we can date back to, say, 50,000 years, 55. And luckily enough, we can do that now. So over the past decade or so, we've been able to expand the calibration curve from what used to be 14,000 to 26,000 years ago, and now and then to 50,000 years ago, and now to 55,000 years ago. And we do that by having more tree rings of floating rings, so floating data sets that are not linked precisely and exactly to calendar years. Varved records, we have, say, annual laminations, and within there have material that can be radiocarbon dated. One of the sites is Suigetsu in Japan, which has beautiful laminations and nice macrofossils of leaves that can be dated and result in quite good radiocarbon dates, although with quite a bit of scatter. And we've also the Cariaco Basin of offshore Venezuela, which also has partly varved records. Then we've also other records like speleothems and corals that can be used as well. So they can be uranium thorium dated. So we have an independent timescale and then also radiocarbon date them. Based on that, we can then extend our calibration curve further back in time. For example, here between 30,000 and 40,000 years ago, we've got a whole range of data sets. The black one here is Chris Turney's Kaori data set, which was published at this 42 Ka record in Science a few months ago. And then we also have Suigetsu in red, which is this Japanese varved lake. And you see quite a bit of scatter of those dates, yeah, especially of Suigetsu. Then the Kariako Basin is in green. And then we've got in blue some corals. Yeah, and the rest is mostly corals. And the further back we go, the less material we have and the more scatter of the dates until we reach around 55,000 years ago, where beyond that, it's still not possible to obtain a good estimate of what the radiocarbon age is for those calendar years. All right. So if we then extend the whole curve, then this is the current Intercal 20 calibration curve. There's really trumpets out here at the end where things are becoming very uncertain. Okay? Right. So what is causing these fluctuations, or these wiggles in the calibration curve? So if we look at, say, the past 100 years or so, since AD 1900, over time, we've got lower and lower, slightly gradually lowering concentrations of radiocarbon in the atmosphere up to around 1950. And that's because at that time, and still, there's lots of fossil fuels which are burned and causing lots of CO2 to come up in the atmosphere from carbon that was deposited millions of years ago and is just devoid of C14. And therefore, we are diluting the C14 in the atmosphere. So you can see, say, the greenhouse effects happening more or less as a proxy of the greenhouse effect or of the CO2 emission. Luckily enough, then we certainly get to very high concentrations, and that is because of nuclear bombs, which were then set off in the 1950s and then especially in the 1960s. And that created lots of new nuclides in the atmosphere, including radiocarbon. We have got almost a doubling of radiocarbon concentration in the atmosphere until the early 1960s, I think 1964 or so, when a moratorium was placed on atmospheric nuclear tests. And since then, concentrations of radiocarbon have gradually come down again. Sorry. If we look at that in radiocarbon years, we see here again, we've got in blue the calibration curve, Intercal 20. And since 1900, we've got like a steady increase in radiocarbon years because we'll get older and older years, even though we go to younger ages. This is years AD. If we go to, even though we go to younger ages in calendar years, we get older radiocarbon ages because of this dilution effects by emission of old carbon into the atmosphere. And then we've got this sudden sudden input of lots of radiocarbon into the atmosphere, new radiocarbon because of the nuclear explosions. And it's such an increase that we can't actually use the same axis to see the blue and the green. So the green data set here, the post-bomb data set is, and we have to plot it on a totally different radiocarbon timescale. And we have to plot it we get very modern years to say minus 5,000. And since the moratorium, then we get back to more recent age. We're getting back to zero again. Okay. Am I lagging a bit or is it okay?
I think
You're
it's
good
okay.
on my end.
Sorry?
No, I think you're fine.
Okay.
You can put stuff in the chat also.
Okay, because I see myself lagging a bit, but I don't know, it might be just my system.
Can I ask a question on the minus 5,000? What are the units of that? Minus 5,000, what is that?
Radiocarbon years.
That's year, wow.
Yeah, and we'll work on that in our just later on. So if you get a post-bomb date, so it's generally not expressed as radiocarbon years anymore. It's expressed as fraction modern carbon or PMC, percent modern carbon. But if you express it as radiocarbon years, you get to minus 5,000. Ridiculous, but that's what happens because of this enormous enrichment. Yeah, compared to 1950. All right, so in different parts of Earth, you will see different expressions of this peak in radiocarbon, the bomb peak. And it's most expressed in the Northern Hemisphere, where there were more tests, I think, and also more landmass. Whereas in the Southern Hemisphere, which is yellow here, there's more ocean, so more of the carbon C14 could be just taken up and absorbed by the oceans. So we see less of a peak there. And in very oceanic sites, you see very little of a peak. Is there a question? No? Okay. Let's go on. All right, so what we can do now in R, instead of writing our own functions, we can use functions of existing R packages. But in order to do so, we first have to load that package. So there's a new package that I wrote over the past year or so, which is intcal. Originally, it was just a package to contain all the calibration curves. But now I've also added some functions to also plot the data, which I think is fun. So we load the intcal code by typing require, if I can. So to load the code, you can either use require or library. And I tend to use require because it types better for me. And I type REQ and then use tab to fill out that command. And then I open my brackets and I type int cal with capital I and capital C. And I close the bracket. Oh no, it's echo. Oh, it's gone. Okay. So, and then I press enter. So that loads the code. Now, and then the next line I want to do, so if you can try to go along with it, with this, we type int cal in all lowercase dot data. And that's a function to plot the int cal data. And we want it from 0 cal BP to 1,000. And then we press enter. And then we end up with this graph here, which we already saw in the presentation. Yeah. So we can also adapt it to be between 0 and 100, for example, and then you can see all the detail of the different data sets that go into producing that blue curve. Yeah. You can also go to older ages between 30,000, 33, and 40,000. That's this here. Yes, very nice, isn't it? Yeah. And we can also draw the curve itself, which is a function called draw.c curve, calibration curve. You can just open brackets, close brackets, and then we have the curve here. And we can also go for different parts of the curve. For example, by saying draw a curve between 1850 and 2020, but that's not in years cal BP. We're saying that this is actually in years BCAD. So we have to tell that we're wanting to work with on the BCAD scale in this case. And then close the bracket. Yes, Rosie, you have to wait. Now you can't keep me. Okay, so here we have then the intcal 20 curve, yeah? Okay, I think in 5 minutes I'll just have to go and feed her, but might also be good for us to have a short break. So here we have just the Untitled Chapter, and we can add another curve to it by typing CC2, so the second calibration curve, and we're using the post-BOM curve here for the Northern Hemisphere Zone 1. So we go back to the previous command, and we add an option CC2 equals quotation mark NH1, another quotation mark. And that gives us this, yeah? So here, both curves are on the same radiocarbon scale. And you can see how enormous the changes in post-BOM curve are, yeah? Compared to the pre-BOM, where the change in the concentrations have been very limited compared to what we have seen since 1950. If we want to place them on two different axes, then we can simply add ADD dot y-axis equals true. We can say true or just a T. And now we have them on two axes, so we can see a bit more detail in either data set. Yeah. Thank you. Oh, thank you. Thank you. Okay. I hope that worked, that you were able to produce some of these plots as well. Yeah. Okay. Now, let's do a few more minutes just looking at reasons of why radiocarbon concentrations have changed in the atmosphere. So we already went through, say, the past 60, 70 years where we've got human-made changes in radiocarbon concentration, but there's also natural changes. And much of that has to do with changes in the geomagnetic field. So in this graph here, we see the Earth, and around it is this magnetic field. And it's a combination of the solar magnetic field, which are these vertical lines here, and the geomagnetic field, which are these lines. And together they make this shield around the Earth, which is quite effective against cosmic rays entering the Earth and producing radiocarbon. It's quite effective. But this shield, this geomagnetic field, and also the solar magnetic field is not entirely constant over time. And sometimes when it changes, it will cause changes in the effectiveness of this shielding. And that will then cause either more or fewer cosmic rays to be able to enter the Earth and produce radiocarbon. Okay. So if we look at, for example, here, here's a graph of the amount of C14 produced per centimeter square per second against latitude of the Earth from polar regions to equator, and then again the other polar region, and then the altitude from 10 to 20 to 30 kilometer height. Yeah, and we can see that in the equator, where the geomagnetic field is very strong, and there's very few cosmic rays that can enter and produce radiocarbon atoms. But at the poles, where the magnetic field diverges, there much more chance for cosmic rays to enter and produce radiocarbon. Especially so when the sun is at a sunspot minimum, which then causes less solar magnetism, and then a less effective shield against cosmic rays. So more cosmic rays can enter and more radiocarbon can be produced. And during a solar maximum, there's less of that produced. Yeah. Okay. And there's also the geomagnetic, say the Earth magnetic field, which also changes over long time scales, and also sometimes within a few hundred years. And generally, the geomagnetic changes are followed quite well by radiocarbon concentrations. Okay, good. I think, do we want to have a break now so I can feed the cats and be back in 5 minutes?
Yeah, I think that would be perfect.
Excellent. Okay, I'll stop sharing the screen then for now. And
thanks. And as some of you, so this is Amy, as some of you saw in the chat, I'm having my Zoom is freaking out in a way that I have never seen before. And so I'm gonna end the meeting and restart my computer and then come back. So I apologize, but you'll need to log in again. Give me probably 5 minutes, which is about the period of our break.
Great. Thanks, Amy.
And I will also put up a poll about the pace of the course at that time when I come back. Okay, thanks. Have a good break. We'll be back around 6 or 7 after the hour.